So my name is Annika, and this is Chapter 2, Motion in One Dimension. So when we're looking at motion in one dimension, there are three main components. There's displacement and velocity, acceleration, and falling objects. So we're going to look at all three of these today, but first let's take a closer look at displacement and velocity. So when we're studying displacement, the first thing to do is choose a frame of reference. This is a fixed perspective that you use to measure changes in position. For example, if we're measuring the motion of a car on the highway, our frame of reference might be by the side of the road, watching the car move. This allows us to measure the changes in position of the car, delta x. And we have to always make sure that the frame of reference is fixed for the entire problem. So once we know the frame of reference that we're using, a key variable in studying motion in one dimension is displacement. Displacement, which we write as delta x, is the distance between the final position, x final, of the object and the initial position, x sub o. This value can be either positive or negative depending on the direction in which the object is moving. So for instance, if we have an object moving from point A to point B, we're measuring the displacement this way, we can say that that displacement is positive. But if the same object moves back from point B to point A, the displacement is now negative. Displacement can also be different from the total distance traveled. For instance, if an object takes a more circuitous path from point A to point B, like this, we still measure its displacement as the shortest distance between point A, its initial position, and point B, its final position. So that's displacement. Alright, once we know the displacement of the object, the next step is calculating the velocity. The velocity is the object's displacement, delta x, divided by the time that it takes for that displacement to occur. Say a car is traveling 6 meters east, distance of 6 meters, and it takes that car 3 seconds. We can find its velocity by dividing displacement, 6 meters, over time, 3 seconds. We get that the velocity is 2 meters per second. Like displacement, velocity can be either positive or negative depending on the direction in which the object is traveling. Let's look at the same car. The car is now traveling back towards the west, again a distance of 6 meters, and it also travels in 3 seconds. However, this time, since it's traveling in the opposite direction, we treat the displacement as negative. So velocity is now negative 6 meters over 3 seconds, negative 2 meters per second. Another way of measuring velocity is to represent it on a graph. Let's take the situation in which the car is traveling to the east. So we have the same car traveling east, a distance of 6 meters, and it takes place in 3 seconds. So we're going to graph the car's position, x of t, versus the independent variable, which is time. So position is the dependent variable, time is the independent. Alright, so we know that the car travels 6 meters, so we'll put that 1, 2, 3, 4, 5, 6. That'll be the position in a time of 3 seconds. 1, 2, 3. And then we can draw that point on the graph and draw a smooth line to connect those 2 points because the car is traveling at a constant velocity. So we know that the slope of any graph is rise over run. In this case, the rise here is 6 meters, and the run is 3 seconds. Therefore, we can see that the velocity is equal to the slope of this graph because the slope is 6 meters over 3 seconds, 2 meters per second. So that's just another handy strategy for measuring velocity that you'll have to keep in mind. So now that we've studied velocity and displacement, let's look at a few practice problems. Number 1, a child pushes a shopping cart at 1.5 meters per second. So we know that this is the velocity. We can label that 1.5 meters per second. How long, so we're looking for time, t, will it take for the child to push the cart down an aisle that is 9 meters long? So we know that's delta x. We can also draw that in here. Delta x, 9 meters. So we know that velocity equals delta x over t. And we also have two of those values given to us. Those values are velocity, which is 1.5 meters per second, and delta x, which is 9 meters. Now all we need to solve for is the variable t, time. So you can see we can multiply t over to this other side. 1.5t equals 9. Divide both sides by 1.5. And we see that t equals 6 seconds. So that's our final answer. It takes the child 6 seconds to push the car down the aisle that's 9 meters long. Velocity practice number 2. An athlete swims from one end of a 50-meter pool to the other in 20 seconds, so that's t, this is delta x, and makes the return trip in 25 seconds. So that's a different t, that's for the return trip. What is his average velocity, A, for the way across? Alright, we'll start with the way across. So we've seen from the problem that the pool is 50 meters across. We also know that the athlete swims across the pool in 20 seconds. So V equals delta x over delta t. That means that V equals 50 meters in 20 seconds. And we can divide 50 by 20 to get 5 over 2, or 2.5 meters per second. So that's part A. That's the velocity for the way across the pool. Now let's look at the way back from the pool. So this time, the distance he's traveling is going to be negative because he's going in the opposite direction. So that's negative 50 meters, and we see that it takes him 25 seconds, a little bit longer. Now we're going to divide again to find that his velocity for the return trip is negative 2 meters per second. So that's part B. Now let's look at part C. So we know that the athlete overall travels across the pool in this direction and then travels back. So he's getting back to this exact same place where he started. That means that the overall displacement of the athlete is 0. So for part C, if the total displacement, again, that's different from the distance traveled, because you can see he takes this circuitous path from point A to point B, but point A and point B are in the same place. So that's 0 meters over the total time would be 45 seconds, because that's the time for the way out plus time for the way back. So that's going to be 0 meters per second. So you can see that even when in part A and part B the athlete had a velocity that was greater than 0, if his total displacement is 0 meters, then his average velocity for the entire trip is 0 meters per second.